Mhm. Okay, good morning. So, so today we will talk about today's tutorial will be about the exam one solution. So, so I will give high level idea how to solve the problems. So some of the details are missing. So if you're interested, yeah, please fill in the details by yourself. So let us review the questions. So the first one is we have a proposition like this, and then we want to find a way to simplify this proposition. So there are various ways of doing so, and I think the most straightforward way is to use a truth table because we don't need to think much about it. So we draw the truth table here. So this is the formula that we are looking at. P implies Q if and only if P and Q. And then we try to evaluate what is the truth value of this one under different conditions of P and Q. So let's write down PQ to be true, 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 false, false, true, and false, false. There are only 4 cases that we need to consider. So P implies Q would then be true, false, true, true in these corresponding cases, and P and Q will be true, false, false, false. And once we have this one and this one, then we will have this one if and only if this one. So it is true when this is true, true, false, false. So we have true, true, false, false. Now the problem here is we now know the scenario of the truth value under these different settings. So can we find a simpler expression to represent this one instead of writing a long one? So is there an expression that we will have true, true, false, false? Now the answer is here. Actually, you will see that it is exactly the same as P. So for this question, the answer is P. So P is the simplest form that we can make for this proposition. Okay, so I hope that Q1 everyone should be able to do this. Of course, you can. So suppose that you have some feeling that when you see this, you have a feeling that this expression will be equivalent to P. Then you can also show this by using the logical equivalences. You can prove this by cases. So we want to show that this is exactly the same as P, so we try to test what if P is true. Now when P is true, then this part and this part will be the same as Q and Q. So P implies Q, true implies Q will be Q, P and Q will be Q, so Q if and only if Q will be true. So when P is true, then the whole thing is true. And when P is false, the first part is going to be false implies Q. False implies Q must always be true. And then false and anything must always be false. So we will have false if and only if true. So which is equal to false. So when P is false, the whole expression is false. So we will see that. Okay. So after these two arguments, we will see that no matter what happens to this expression, the value of this expression must be the same as P as always. So in that case, so this is equivalent to P. Okay. So you can use the truth table or you can use logical equivalences. Now the second question asks us to see to prove or disprove two cases. So the first one is x and y will have domain of integers. Okay, so we want to ask, is it true that for every integer x we can always find y such that y is smaller than x, but then x and y after their multiplication it will always be greater than or equal to 0. So in this case, yeah, it is true. Yeah, you can prove it by cases. So at any for all the cases, we just simply choose y is equal to x minus 1. It will work. You can have your other solution. It is not the only solution that we can, but we should be able to argue that it is true. Okay. But on the other hand, we have a slightly different proposition. So it is saying that for every integer x, we can always find y such that y is smaller than x, but then xy is strictly greater than 0. Now, for this one, we will see that when x is equal to 0, there is no such y because when x is equal to 0, then xy will always be equal to 0. So you cannot find something that makes xy greater than 0. So in this case, when x is equal to 0, we cannot find y. So when x is equal to 0, we have a counter example that it is going to be false in the remaining part. So in that case, the whole expression, the whole proposition will be false. Okay, now for question number 3, we have 3 positive integers x, y, and z, and then it is known that x squared plus y squared is equal to z squared. We want to show that either x or y, or both actually, either x or y, it means that we can include the case both, is divisible by 3. Okay, so at least one of them is divisible by 3. So how do we show? So this is going to be a simple exercise. So we can actually prove it by contradiction. So because we are talking about what? We're talking about divisible by 3. So let us classify the numbers based on the remainder after division by 3. So all the numbers, you can now see that they are either a multiple of 3, or 1 plus a multiple of 3, or 2 plus a multiple of 3. So we can see that for any integer, if we square it, making the square of an integer, so that after squaring it and then divide it by 3, then it will always have remainder either 0 or 1. So we have done this already in lecture notes 4. And then this is actually not difficult to show. You just prove it by cases, right? So a square number, when divided by 3, will always have remainder 0 or 1. Okay, now we try to prove this by contradiction. So what do we say? So we shall assume that x and y, so we assume this is wrong. So we assume x and y, they are not divisible by 3, both of them. So it is not divisible by 3, this is not divisible by 3. So in that case, the square of x when divided by 3 will have remainder 1. The square of y when divided by 3 will also have remainder 1. So divided by 3 remainder 1, divided by 3 remainder 1. So what does that mean? It means that the z squared will have remainder 1 plus 1 when divided by 3. So we will have z squared will have remainder 2 when divided by 3. And now we have a contradiction. Why? Because a square number cannot have remainder 2 when divided by 3. So a contradiction occurs. Now we have another related problem. So the question setting is the same, except that we want to show that either x or y is divisible by 4. Now, of course, we have success in showing that how do we show division by 3? So we consider numbers based on the remainder after division by 3. But if you want to do the same thing here, you will hit some problem. Because when a square number is divisible by 4, let me see. A square number, when it is divisible by 4, then what? Then it can have remainder 0, or it can have remainder 1 only. But then it's not enough to say that. So it's not enough. So you will hit some trouble when you try to use divisible by 4. Perhaps you will need a more tedious argument to show. Because what we can show, if you go along the proof, you will say that if x and y are both not divisible by 4, there are actually 3 different cases. So x could be a multiple of 4 plus 1, x could be a multiple of 4 plus 2, and x could be a multiple of 4 plus 3. So when we have x and y both to be a multiple of 4 plus 2, then you don't see any contradiction immediately. So in that case, we are going to do something a little bit different. So this is our idea. So instead of looking at division by 4, so we slightly make this, so the tricky part here is we look at the square of an integer when it is divided by 8 instead. So 8 is related to 4, but we are not using 4 directly. Now when a number is divided by 8, the square of a number is divided by 8, then the remainder can only be either 0, 1, or 4. You can prove this by cases. Okay, so I'm not going to give you all the details, but this is a high-level idea. So first of all, we will see that when a square number, is divided by 8, the remainder must either be 0, 1, or 4. Now here, we suppose that to the contrary, that x and y are not both, so they are both not divisible by 4. So both of them are not divisible by 4. So what will happen? Now we know that z squared is a square number, so it must have remainder either 0, 1, or 4. Now if z has remainder 0, 1, or 4, then the possible remainders of x squared and y squared when divided by 8 could only be, let's say this is the remainder for x squared, this is the remainder for y squared. So it could be 0 and 0, because 0 plus 0 you get a 0. Or 0 or 1, you get 0 plus 1, you get a 1. Or 1, 0, 1 plus 0, you get a 1. And then actually, I've forgotten. So it could be 0 and 4, and then 4 and 0, and also 4, 4. But what I'm saying here is that, so I will make this updated. Okay. So what I want to say is that if one of these x squared or y squared has remainder 0 when divided by 8, then it must be a multiple of 4. A multiple of 4 will have remainder 0. A multiple of 4 plus 2 will have remainder 4. And all the other case, it will have remainder 1. So this 0 must come from a number which is divisible by 4. So in that case, we have a contradiction. The contradiction comes from x and y are both not divisible by 4. Okay. So the only case that we need to discuss is x squared and y squared. They will both have remainder 4 here. So when x and y after squaring will have remainder 4, so what could these numbers be? So this is the last case, 4 and 4. So x can only be a multiple of 4 plus 2. So in that case, x is equal to 2 times an odd number. And similarly, y has remainder 4 is also equal to 2 times an odd number. So that after squaring it, it will have remainder 4 after division by 8. But for that must be 2 times an even number because, because z squared is a number that is divisible by 8. So z must be actually a multiple of 4. So it is 2 times an even number. So if this is the case, then what we can do here is that originally we have x squared plus y squared is equal to z squared. And what we are going to do is let's cancel the 2 here. We cancel the 2 here. So we make x and y and z half of its original value. So by doing this, we will still have x squared plus y squared is equal to z squared. But now, x this time is an odd number, y this time is an odd number, and z this time is an even number. And we will get a contradiction because the remainder of x squared when divided by 8 will be 1. The remainder of y squared when divided by 8 will also be 1. So 1 plus 1 is equal to 2, and 2 cannot be a remainder of a square number when it is divided by 8. So we get a contradiction. So this is question 3b. So okay, the next question, okay. So the next question is, suppose that we have k, m, n, they are all positive integers, and then we have told you that 1 over k must be equal to 1 over m plus 1 over n. We want to find out for any k greater than 1, 2 pairs of mn that will satisfy this formula. Okay, so one of these mn will be very easy. So this is k, 1 over k. So you can set m and n to be 2k, 2k. So 1 over 2k plus 1 over 2k will add up to 1 over k. So this should be easy. Okay, how about the other case? The other case is also it's a bit tricky, but you can just trial and error. So first of all, we know that these two values has to be greater than k, right? Yeah, because you add up to 1 over k, so neither of them could be less than or equal to k. But what we can try here is, let's try m to be the smallest number that is greater than k. So what is it? It is k plus 1. So it is going to be k plus 1 that we try here, and then what will happen? So we're asking if it is possible to find an n such that 1 over n is equal to 1 over k minus 1 over k plus 1. And it works. So you can set n to be k times k plus 1, and it will work. So we have two pairs. Now the tricky question here is this one, question 4c. So here we want to say that if k is a prime number, then there are only two pairs of Mn. So the previous case that we find, they are all the possible pairs of Mn when k is a prime number. So how can we show this? So we can show this by somehow a direct proof. So first of all, from this equation, so let us multiply. So let us try to make all these fractions disappear. So we multiply m and k on both sides. So the left-hand side will become m times n. This one will become nk, and this one will become mk. So we will have mn is equal to kn plus kn. So we can easily rearrange the formula to have mn minus km is equal to 0. Now, if you notice this one, this is very, very similar to something like m minus k multiplied with m minus k, right? So the missing term here is that we should add k squared so that we can complete it, so that we can make it into something like this. So after adding k squared on both sides, the left-hand side we can factorize it into m minus k times m minus k, and the right-hand side is k squared. Now recall that k is a prime number. So this is the square of a prime number. And then I tell you that there are two integers. After multiplying them together, we will have the square of a prime number. So what can that be? So we can have one of them to be 1 and the other to be k squared. Or both of them is equal to k. So these are the only two cases that we have. So in the first case, then we will have m is equal to k, and then m is equal to k plus 1, and then n is equal to k times k plus 1. And for the second scenario here, we will have mn both to be equal to 2k. So for this question, so you need to have some basic understanding that, so if we want to find numbers such that, to find positive integers such that their product is equal to the square of a prime, then there are only two possible ways. So this comes from the unique factorization theorem of an integer that we might have studied in our primary school, but maybe we didn't show this to be correct then. Yeah, but we know this. Yeah. Okay, so this is question 4c. Now, question 5 talks about a game. This is a stone picking game. So we have n stones initially, and then there are two players playing this game. And then each turn, a player must take either one stone or two stones. And if at a particular turn that the player is going to play and no stones are left, then the player loses. So we want to show that the first player wins if n is not divisible by 3. Actually, if and only if n is not divisible by 3. So how do we show? So this is not super difficult. So let's understand why when n is a multiple of 3, the first player will lose, no matter how smart the first player plays. Now, it is because suppose that n is a multiple of 3. So let's say n is equal to 21. So no matter what the first player, let's say Bob, plays, the second player must play the stone such that it adds up to 3. with whatever Bob just played. So if Bob plays by taking 1 stone, then Charlie, let's say the second player, takes 2 stones. On the other hand, if Bob plays by taking 1 stone, 2 stones, then in that case, Charlie will take 1 stone. So no matter what happens, Charlie will make sure that the number of stones that he takes, adding up with Bob in that turn, will be equal to 3. So in that case, after each turn, Charlie will make sure that when it gives back to Bob, it will be 3 less than the original. But if the original number n is a multiple of 3, then Charlie will then win because after let's say 21, right? 21 is equal to 3 times 7. After 7 rounds, Charlie will make the total number of stones decrease from 27 back to 0 and put this back to Bob, and Bob will lose by then. So we see that if n is a multiple of 3, then the first player will lose. So on the other hand, if n is not a multiple of 3, then the first player can always win by what? By taking enough number of stones, 1 or 2 stones, so that the resulting number will be a multiple of 3, putting the other player to lose. So this is the idea of this question. Okay. So the key idea is you find a good strategy for the second player if the total number is a multiple of 3, and you find a best strategy for the first player when the total number n is not a multiple of 3. Okay, so these are all the questions that I want to cover today. And actually, in the exam, there is a question number 6. Okay, so where is the exam paper? Let me see. Okay, question number 6. I don't want to give you the proof directly here. Okay, so question number 6 is like this, right? So you have 3 boxes. 3 boxes. So there are signs on the box. Let me make it larger. Let's see. Let me make it the largest possible so that you can see more clearly. So we have 3 boxes, and then each of the box there is a sign, and then we don't know whether the sign is writing something correct or wrong. So all of them we don't know. Some of them could be right, some of them could be wrong. We don't know. But what we know is that one of these 3 boxes contains a treasure. This is what we know. And then we want to find out which box contains the treasure if we can do so. Okay, so how should we do? Okay, so for this type of question, there is always one very easy way to show. We try all the possible scenarios. So we try all the cases where, let's say this statement is true, this statement is true, this statement is true. So we see that when this is true, 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 can we know or can we deduce where is the treasure, or are there any contradiction? And then after we try true, 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 we try true, true, false, and then true, false, true, true, false, false. So altogether, there are 8 cases that we need to try. And then if you are careful enough, you will find that out of these 8 cases, 7 of them cannot happen. So you will then see that you can find out exactly what is the particular case and then deduce where is the treasure. Okay, but then there should be a shorter, okay, that is the most straightforward proof. It is just like using a truth table. But then for this question, we can also show this by some logical arguments. So it is like question number 1, but then we try to show it by using logical equivalence. So first of all, let me give you some hints to begin with. Okay, so let's see if we can show this by using logical equivalences. So first of all, the key idea here, we can simplify this problem is that we will argue that box 3 cannot have the treasure. Now, if box 3 has the treasure, then there are 2 cases that we need to check whether it is possible or not possible. So our claim here is that box 3 cannot have treasure. The reason is like this. So if the statement of box 3 here is true, then it says that for the box with treasure, the sign on it is false. So if this is the case, if we assume that this is the sign which is true, then this cannot be a box with treasure because it says that the box with treasure, the sign of it must be false. So in that case, you cannot have a treasure on it. Now suppose that this statement is wrong. So what does that mean? So it means that for the box with treasure, the sign on it, let me see. Let's say this is false. And then, so the sign on it is true. Let me see. So what will happen? So in that case, this is false because this is false. And then what it says is false. So the correct thing will be for the box with treasure, the sign on it is true. Okay, so this is the correct scenario. All the box with treasure, the sign will be true. But we have assumed that box 3 has a sign which is false already, so it cannot have treasure in this case. So by logical arguments, we can really take out some of the cases that we need to talk about so that we can argue that box 3 cannot have treasure. So for this question, it is quite fun. So see if you can have a logical deduction of how you can arrive the conclusion of what will happen. But of course, if it is during the exam when the time is limited, yeah, for this particular example or for this particular question, I really recommend you to use the truth table technique. Try all possible cases, true, false, up to false, and see what will happen. Okay, so that's all for the discussion for today. Okay, so let me see if you have any question. Let me see. Oh, oh, yeah. I hope you liked the exam. Yeah, it's a little bit hard for some of the tricky questions, but I really hope that every one of you can get something like 80 plus. Okay. Okay, I think, yeah, that's all for what I want to talk about today. I will upload the revised PowerPoint to you at EE class, and then let's see again next Monday for tutorial on week 7. Okay, that's all. Thanks. Treasure, I think so. I forget. Yeah, I think so. Yeah, thank you very much. Yeah. Eh? Okay, so let me close my terminal now. Yeah, I forget how to close it. Okay, so let me close it. Okay, see you next time.